Satish. Satish ji.
1 second, sir.
Okay, sir. Okay.
Satish, you are in line.
Sir,
Chetan,
One
Chetan.
second, sir. One second, sir. One second.
Yeah, enable Satish.
I'm just working on it. 1 second, sir.
Yes, please. 1 second, sir.
Yeah, now Satish ji can unmute, sir.
Satish.
Good morning, sir.
Good morning, Satish. You can go. You can proceed now. Satish, you are in line.
Thank you, sir.
Yeah.
Yes, sir. Yes, sir.
Chetan,
One
Chetan.
second, sir. One second, sir. One second.
Yeah, enable
I'm
Satish.
just.
Start ಮಾಡಿ. Hello.
Satish.
No, I think.
Sir, good morning, sir.
Good morning, Satish. You can proceed, Satish.
So shall I start?
Yeah, 1 second, sir. 1 second.
Sir, sorry.
Yeah.
Okay. A very good morning to everyone, all delegates, esteemed scholars, and the participants. Welcome to the 5th day of national level workshop on research techniques and applied econometrics, organized by Department of Economics and Research Scholars Forum, Department of Economics, Davangere University, Davangere. The illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn. Alvin Toffler. Myself, Satish P., research scholar, Department of Economics, Davangere University. It's given me an immense pleasure to welcome you all. First, let me welcome Dr. K.B. Rangappa, Professor, Chairman, Department of Economics, and Dean Faculty of Arts, Davangere University. On behalf of Research Scholar Forum and Department of Economics, sir. I take privilege to welcome today's speaker, Dr. Professor of Economics, University of Mysore. On behalf of Research Scholar Forum and Department of Economics, I welcome you, sir. Let me welcome Dr. Sitra S., Associate Professor, Dr. Selvi Or, Associate Professor, Dr. Uche Gowda, Associate Professor of Department of Economics, Davangere University, to this workshop. Not least, I welcome all esteemed scholars and participants to today's workshop. Let me give brief introduction about today's speaker, Dr. Mahesh S. Dr. Mahesh S. is a distinguished professor of economics at Department of Economics and Cooperation, University of Mysore, Mysore. He holds a PhD in economics. He is specialized in quantitative methods, applied econometrics, efficiency, and productivity analysis. Professor Mahesh has published more than 40 research papers in reputed journals. More than 50 papers have been presented at national and international conferences and seminars. More than 10 research papers have published in edited books. Professor has published more than 5 books. He is also working as member in different academic bodies in different universities. 9 MPhil scholars and 7 PhD scholars were awarded degrees under his supervision. Presently, 6 PhD scholars are pursuing research under his supervision. A lot said to you about Dr. Mahesh. Due to time constraint, I highlighted important one. Hope today we will have a fruitful session. Thank you. Over to Dr. Mahesh, sir.
Okay. Thank you. Thank you very much, Satish. Okay. Let me start today's session. The today's session is on the qualitative response variable models or dummy dependent variable models. In the last sessions of this workshop, especially when Rangappa sir started his speech on regression analysis, you have learned the use of regression analysis in our field. And also the regression analysis is used as a causality tool or measuring cause and effect relationship among the variables in many disciplines, even in pure sciences like physics, and also in medical sciences. When we make use this statistical tool, that is regression analysis, as a tool of measuring causality, cause and effect type of relationship. So normally, as a rule of thumb in development of a theory, the same is followed in case of the use of regression analysis also in econometrics. Hence, I hope Rangappa sir has discussed about the simple and multiple regression models and their applications in specifically economics research. But in that introductory part of application of regression analysis in economics or in any discipline, one of the implied assumption, okay, it is an implied assumption, it is not an assumption of classical linear regression model. It is an assumption because of to make our learning of the regression analysis and the application of regression analysis as parsimonious as possible or as simple as possible. So hence, I think Rangappa sir has started his speech with a simple regression model by using only two variables, one dependent and one independent variable, and extended straightforward that regression into including many independent or explanatory variables. So then he called, of course, we called that model as a multiple regression model. But in both of those two cases, where both the dependent and explanatory or independent variables are assumed to be quantitative in nature, I hope many of you have a knowledge of types of data in statistics, and that has been classified based on several criteria, like the number of the variables, and also the measurement scale of the variable, and so on. On the basis of the measurement scale of the variable, as of course we were noted that, or we have learned that the variables or the data been classified into nominal data, ordinal data, interval data, and ratio scale data. And these four measurement scales can also be clubbed and classified into two groups or two classifications, like the quantitative variables and qualitative variables. Okay, quantitative variables and qualitative variables. And in the previous classes related to that regression analysis of simple and multiple regression analysis, both the dependent and independent or explanatory variables are assumed to be only quantitative in nature. So like the salary is a function of level of education, or it is based on experience, or consumption is a function of income, or investment is a function of interest rate, and so on, so on. So the variables just I have mentioned are all quantitative variables. They are measurable variables. So they are have a metric measurement. But we know that in practice, a variable, or our purpose, of course, in regression analysis is to measure or to estimate the mean value of the dependent variable from the fixed or given related independent variables. But we know that not always a variable, for example, a quantitative variable, not always influenced only by the quantitative variables. There are situations, circumstances in practice where a quantitative variable is also influenced by qualitative variables. For example, if you take the wage discrimination, the discrimination in wage between male and female, so then you should have to consider gender as one of the factor influence on the wage rate. So if you include a qualitative variable like gender or a race or a religion or a caste and so on, such qualitative variables in the right hand side of your regression analysis, that is independent dummy variables or independent qualitative variables, along with the quantitative variables. So then we call in econometrics those models as the dummy variable regression models. So in case of the dummy variable regression models, your dependent variable is a quantitative variable like salary, whereas the independent variables are a combination of both quantitative and qualitative variables like experience and gender. Experience is one of the factor influences on salary or the wage rate, whereas the gender is a qualitative variable or a categorical variable. If you have only include qualitative independent variables into your regression model, so that is equivalent to your analysis of variance which have been studied in your statistics. But if along with that qualitative variables, if you include covariates, so these quantitative variables also known as covariates in statistics. So along with that qualitative variables, if you include quantitative variables or the covariates into your regression analysis, so they are called as UNCOVA models in statistics. UNCOVA, that is analysis of covariance models. The covariance means, so you are measuring the changes in the dependent quantitative variable, both because of a qualitative variable or a group of qualitative variable and also a set of quantitative independent variables. So they are called as UNCOVA models. But in econometrics, so there is no such classifications of ANOVA or UNCOVA. Generally, we call these models as dummy variable models or dummy variable regression models. So these dummy variable regression models, they include the qualitative variables as explanatory variables, but you have continued to use a quantitative dependent variable. So this is the just distinction between your simple and multiple regression model with the dummy variable regression model. The difference is your right hand side of the equation or your some of your explanatory variables are qualitative variables, and except that your specification of the model, your estimation of the model, and your hypothesis testing of the model is straightforward. That means there is not difference between these okay, a qualitative independent variable models along with the quantitative variables and a general simple and multiple regression models. The difference and another difference is in terms of the interpretation. In terms of the interpretation of the coefficient of a dummy variable or intercept dummy, actually that is called in dummy variable regression model. So that is not part of my discussion today, because we normally use the dummy variables in our regression analysis, either in the right hand side of the equation or in the left hand side of the equation, in some cases in both the sides. So my discussion or my today's discussion is related to the one more modification to our regression analysis, where our dependent variable itself is a dummy variable. Dependent variable itself is a dummy variable. So that's why, so statistically, that is strategically, these models are significantly different from your earlier models like simple regression model, multiple regression model, and dummy variable regression model. Because in all these three models, your dependent variable was a quantitative variable, but whereas in case of the today's qualitative response variables model or the dummy dependent variable model, the name itself indicate your dependent variable itself is a qualitative variable or a dummy variable. Dummy variable. Once we introduce or modified our regression model by incorporating a dummy dependent variable, so we cannot continue with the earlier methodology, either of estimation or of interpretation. Okay, so we should have to follow a distinct, a separate procedure for these qualitative response variable models or dummy dependent variable models. So hence the dummy dependent variable model or a qualitative response variable model is a model where the dependent variable of your regression model is a qualitative variable. It is a dummy variable, and of course all of you knew the difference between the concept of qualitative and a dummy variable. The qualitative variable cannot be directly measurable. For example, gender, race, then religion, caste, and so on. They cannot be directly measurable. Willingness to pay, or whether a person is willing to work or not, or is employed or unemployed. Like that, there are several such innumerable examples we can give for such qualitative variables in economics that cannot be directly measurable. Hence, they are called as qualitative variables. So since these qualitative variables are also as equivalent as quantitative variables in econometric analysis and also in economics, defect type of relationship among our chosen variables cannot directly include these qualitative variables. We need to convert these qualitative variables into a dummy variable by assigning some values, by coding these qualitative variables. And I hope all of you are familiar with that coding of a qualitative variable in terms of codes like 0 and 1. 0 indicates, 0 represent absence of the attribute or the quality of the chosen variable. 1 represents or indicates the presence of the attribute. For example, if you take gender as one of your qualitative variable, so then for example 1 indicates male, 0 indicates female. Okay, so likewise if you take the race, so then the race white, non-white. 1 indicates white, 0 is otherwise. So that is the non-white. So if we code the qualitative variables with some codings, normally with 0 and 1, so then we call that variable as a dummy variable, because the 0 and 1 which we have coded are used to code that qualitative variable has no meaning. Hence the value of that 0 and 1 are dummy. So hence they are called as dummy variables, and we use that 0 and 1 are dummy variables as a dependent variable in these types of models. Okay, in these types of models. So now let us have a brief discussion on today on these qualitative response variable models or dummy variable models. So there are different models within these qualitative response variable models or dummy dependent variable models. So I will take the few and the most widely used in practice. And there are of course the 4 such models which have been used in practice related to the dummy variable model, like linear probability model. The second one is logit model or logistic regression model. The fourth one is probit regression model or probit model. The next one is tobit model. And of course, even with this a qualitative variable, whether it is a dependent or independent variable. So not always we have only two categories, only two classification of a variable. So we can have as many as the characteristics that possessed by a variable, and based on that we can classify a qualitative variable into different categories. So like for example, employed and unemployed. So it is a dichotomous variable. Actually it is called dichotomous means so only you are able to classify your variable as employed or unemployed. Whereas in case of a person, whether the person is employed in agriculture, whether he's employed in industry, whether he's employed in banking sector, whether he's employed in any other sector or not. So now you have multiple of choices, So they are called as multiple choice model or multiple choice models, or for that we have to use different other types of models, multiple logit models, multiple probit models, and so on. But our discussion today is related to the simplest part of that dummy dependent variables, having only dichotomous in nature or only binary in nature. Binary means, so only we have two classifications, so the 0 and 1 or 1 and 0, and it is only an arbitrary. There is no any hard and fast rule to always you should have to assign 0 and 1 or 1 and 0, but it is left to the researcher. You are free to assign 0 and 1 for your qualitative variable. So now let us have a discussion on this, the qualitative response variable models or the dummy dependent variable models. So in that, the first model is the linear probability model. And one of the important point which you should have to bear in your mind, why the probability comes here, because if you have an indicator or a binary choice, so it is the probability, or the probability enters there. So our purpose here is not to estimate the variation in the dependent variable and measuring that variation for every unit change in the independent variable in case of your earlier regression model or a quantitative dependent variable model, or in other words, very simply, so our purpose of a quantitative dependent regression model is to estimate or to predict the change in the dependent variable because of every unit change in the independent variable. That is not holds good in case of this dummy dependent variable models, because you have only two options, two choices. So we have only two options or two choices. Okay, two choices. So hence it is only the probability, that is the probability of the occurrence of the event and not occurrence of the event. So hence, to understand and to learn this qualitative dependent variable models or dummy dependent variable models, you should have to have some knowledge of probability and calculation of the probability, and also the interpretation of that probability related phenomenons, Okay, so now let us start with the first kind of that. So that is okay. Let's just have told you that so far the dependent variable y in our regression model has been continuous, quantitative in nature, like average hourly earnings and traffic fatality, or any such variables, that is the investment or profit or demand or supply or production. So all these variables are quantitative in nature or continuous in nature. But what if y is a binary variable? That is a, a variable which has two categories, which has only discrete in nature, and also which is as only two categories in or we are able to classify that variable into only two groups. So that variable is called as a binary variable, like y, if the dependent variable is getting to college or not. So we know that there are not all the students who have entered into PUC, so not entered to the undergraduation. So there are factors which are responsible to determine getting to the college or not getting to the college. So if your study, if your work is, if your analysis is related to determine which factors influencing on the students to get into the college and not get into the college, so then the dependent variable itself is a binary variable, and it is getting to the college and not getting to the college. So the one of the variable that assumed to be influence on whether a student get into the college or not is influenced by the income of the parents or parental income. Then one more Example of a binary variable is person smokes, whether a person smoke or not. So that depends upon the income of the person, then cigarette tax rate, that is the tax rate on the cigarette, the price of the cigarette, and so on. These factors influencing on whether a person smokes or not. So where our focus is on the y, that is the dependent variable, that is yes or no, whether the person smokes or not. Then one more example is the mortgage application is accepted or not, because if you go to if your study is related to the loan advancing or the sanctioning by the banks, so the banks receives a large number of applications. Okay, but not all the applicants wouldn't get the loan. So then some applications are accepted for granting loan, and some are not accepted for granting loan. So the which factors determines the acceptance of the application for loan or mortgage applications are accepted or not, like their race, their income, house characteristics, marital status, and so on. So these factors are the X factors, that is the independent variables, determines whether a mortgage application, a loan application is accepted by the bank or not. So the focus variable here is why the mortgage application is accepted, that is yes or no, that is not. And likewise, whether a person is died or not, broke a hip or not, has hypertension or not, whether a person has diabetic or not, whether a person is employed or not, whether a person or a household as having a own house or not, whether a person has owning a car or not. So like that we are, or whether a person is willing to donate for a charity or not. So like that we are able to give a large number of examples in economics where our dependent variable is a qualitative variable or a binary variable. So now the question is, so if our dependent variable y is a binary variable, so like these, what happens to our regression, or how do we go with these dummy dependent variable. So then in case of these above said y, that is the dependent variables, we typically want to understand what is the probability of binary outcome given explanatory variables. So because I hope all of you have studied the mathematics behind the regression analysis, So in case of a quantitative dependent variable, as earlier I have told you that it is the purpose, or our purpose is to estimate the expected value of the dependent variable y for the given values of x. So that can be written mathematically as the E of y given x. E of y given x. The expected value of the y with the given value of the x is determined by the explanatory variables from x1 to xk. That means you are taking all the factors which are responsible in influencing or changing the value of the dependent variable, and you are estimating the average of that change in the dependent variable from the known values of x. So that is the conditional expectation of the quantitative variables or the covariates which you have been studied in your simple regression model, and also in case of your multiple regression model. But whereas in case of this binary outcome variables or binary dependent variables or binary choice models, are simply are generally qualitative dependent variable models. So we should have to understand the probability of the binary outcome given the explanatory variables, or in other words, here our purpose is to estimate the probability of the occurrence of 1 or 0. So earlier I have told you that you have to convert these binary variables or binary choice variables or the qualitative variables into some dummy variables, and your purpose is to estimate the probability of occurrence of 1 and the probability of occurrence of 0. And what is the probability of occurrence of y, which is equal to, okay, 1 when the value of x is given. So hence the probability is entered into our analysis, and we have to use that and estimate the probability of occurrence of the events, the two events, that is yes or no, yes or no. So hence there is a difference in the specification of the equation and the equation. So this equation is and of course, the equation in case of the left-hand side of this quantitative dependent variable model, our modeling is related to conditional expectation, whereas in case of this binary choice models or qualitative dependent variable models in general is to model the probability of the given covariates. So that is the probability of occurrence of the one and the probability of occurrence of zero. So this is the main distinction, main difference between our quantitative dependent variable regression model and this qualitative dependent regression model or binary choice models. Okay, so then how to estimate that probability? Okay, how to estimate that probability of occurrence of the events or the outcomes of these qualitative response variable models. There are different procedures developed by econometricians and come statisticians. Earlier I have told you that they are called as the dummy dependent variable models. So the first among them is linear probability model. The second one is logit or logistic regression model. The third one is probit model or probit regression model. The next one is a special case of all of this is the Tobit model or Tobit regression model. So hence there are different models within this qualitative dependent variable models based on the circumstances, based on the nature and the characteristics of the data. We have to select the appropriate model for our data or for our objective related problem. So now let us start with the first simple model of this qualitative response variable model, that is linear probability model. Linear probability model. The name itself indicates the purpose of this model is to estimate the probability of the occurrence of the choices or the binary choices, and which is assumed to be linear, because I hope you are familiar with that classifications of the regression models in different names, like one among them is linear regression and non-linear regression model. So though our purpose is here to estimate the probability of the model, basically a model which estimate the probability based on the given covariates or the given values of the independent variables is non-linear in nature, but this model assumes the linearity in that. So hence this model is called as LPM or linear probability model. So this is not used in practice, but to understand the next advanced models of this qualitative response are the dummy dependent variable models. So you should have to have a knowledge on this linear probability model. So this is a multiple regression model. That is how this linear probability model has been developed, and also how it is distinct or different from the earlier multiple regression model as given in this slide. The multiple regression model with a continuous dependent variable or a quantitative dependent variable model is specified like this, as you already noted. And as I earlier told you that the coefficient of this multiple regression model beta j, that is the beta 1 to beta k, can be interpreted as the change in the y associated with a unit change in x. That is how much the dependent variable y changes for a unit change in x1, x2, x3. For example, if your model is related to or one example of multiple regression model is like this. So investment, for example, if the investment is y, that is a dependent variable, then the investment is depends upon the interest rate, and the sales, for example, the sales invest. So if you take these two as the independent variables, so then that by estimating that model, you are able to interpret the coefficient of that investment function as if the interest rate decreased by or increased by 1%, how much the investment varies, changes. And if the sales of that particular company increases by a given amount, a unit of change, how much the investment increases, so or decreases. So hence the interpretation of the coefficients of this multiple regression model is a straightforward one, and our purpose is to interpret the change in the value of the y variable or variation in the value of the dependent variable y associated with a unit change in the values of the independent variable. But in case of this qualitative dependent variable models, you cannot follow that procedure of interpretation or the method of interpretation. So we know that as you're already, the expected value of the binary variable y is written. It is like this: the expectation of y, which is equal to 1, that should be multiplied by the probability of occurrence of 1. That is the probability of y is equal to 1. Plus, then there are some situations where the y cannot be occurred or not happens to occur. So then it is 0. Then the 0 into the probability of occurrence of 0. So that's why the expected value of a binary variable or any qualitative response variable model, even in case of multiple choice or multiple multiple cotomous variable or multi-cotomous variable. So it is the probability of that particular variable or the particular outcome. So hence since it is a binary outcome variable, you have only two outcomes. One is success, the other one is failure. The success is here coded as 1, the failure is coded as 0. So hence you should have to multiply that 1 with the probability of occurrence of the 1 and 0 with the probability of occurrence of the 0. So then which is equivalent to the probability of occurrence of y is equal to 1, because if you multiply the 0 with this, so that gives you 0. Then the remaining value is the probability of y is equal to 1, because 1 multiplied by probability of y is equal to 1. Anything multiplied with 1 is the value is same, that doesn't change. That's why this regression equation or this expected value of the binary variable equivalent to the probability of y is equal to 1. So hence in the binary dependent variable model or qualitative dependent variable model, the expected value is the probability of occurrence of your dependent variable y, which is equal to 1, So in case of the multiple regression model with a binary dependent variable, so if you have several independent variables in your binary dependent variable model, then the expected value of your binary outcome, that is yi, given the values of independent variables or the explanatory variables, that is x1i to x1k, which is equal to the probability of y high is equal to 1 given x1 to xik. So which means that the occurrence of the y is equal to 1 or the happening of the y is equal to 1 depends upon several independent or explanatory variables. They are named here as x1 to xk. So by observing this equation, it is a linear model, because you are estimating the expected value of the y for the given values of the x, where your parameters are represented in linear form. So except of course this part and also this probability, so this expression or the equation looks a linear one. So hence you are estimating a probability of occurrence of y is equal to 1 with the given values of the x, and your model specification is linear in nature. Hence this model is called as linear probability model. Linear probability model, or the probability of the occurrence of y is equal to 1 with the given values of x1 to xk. So the functional form which we have been specified to estimate the probability of the occurrence of y is equal to 1 is, since linear in nature, hence this model is linear probability model. So we could actually use our linear model to do so. It is very simple to understand. And why, if y is an indicator or a dummy variable, then expectation of y given x is the proportion of the ones given x, and which we interpreted as the probability of y given x. That is the thing which I already told you, that is here your dependent variable is a dummy variable or indicator variable. So you are estimating the expected value of the y given the value of the x for the proportion change in for 1 unit in x value. And now we have interpreted as a probability of y given the x value. So we can then interpret the parameters as the change in the probability of y when x changes by 1 unit or a small change in x. So that means, the interpretation of this linear probability model is simple and somehow similar to our multiple regression model. So only the difference is, earlier I have told you that we have used a 1 unit change in that is the amount of change in y is associated with the 1 unit change in x, but instead of that now we are using the word probability. That is the probability of y when the x changes by 1 unit change in x. So the same 1 unit change in x has been used, but instead of using change in y, now we are using that as the probability of y, probability of y. For example, if we model died, that is if a person is died or not, that depends upon the age. For example, that is the probability of the person of death. The probability of the person of death, that depends upon several variables. One is the age rate, that is the age age in years. So we could interpret the coefficient beta 1 of this age as the change in the probability of death for an additional year of age, for an extra year of age, for an additional year of age. What is the probability of a person of death? So we know that as the person of the age increases, the probability of death also increases. So that is for every additional 1 year, what is the probability of death of a particular person. So the interpretation of this linear probability model is simple in the terms that simple compared to the next models which we will discuss later, that is the logit model and probit model. And you should have to keep this point in your mind. So how to interpret the coefficient of a binary uh, qualitative dependent variable model in case of this linear probability model. So this is about the linear probability model or LPM in case of qualitative dependent variables. And let us take one example for this uh, uh, LPM model. It is related to mortgage applications. The most individuals who want to buy a house apply for mortgage at a bank. Not all mortgage applications are approved, as earlier I have mentioned. Then what determines whether or not a mortgage application is approved or denied? There are several variables. Earlier we have noted that their level of income, housing conditions, and their race, their experience in the present work. So they are all influences. Okay, they are all influences on whether the application of a mortgage is accepted by the bank or not. So that is the responsibility of the researcher as you to determine or to identify the determining factors. But the point is, so your purpose is here to estimate, here to measure, or to fit a regression model, or to construct a regression model. So regarding the determinants of mortgage applications. So then since your problem is related to determinants of the mortgage applications, you should have to identify the determinants of mortgage applications. And whereas your dependent variable, since it is a mortgage applications, so that some of the mortgage applications are accepted by the bank and some of the mortgage applications are not accepted by the bank. So this is the question or the research questions we are trying to answer. So for this, let us, here in this illustrative example, we have selected a subset of the Boston HMDA data that consists of 2,380 applicants. A data set on mortgage applications collected by the Federal Reserve Bank in Boston. Okay, we have used that data of 238 applicants. And here we have selected three variables, one dependent variable, two independent variables. The dependent variable, as we already noted, is a qualitative variable, a dummy variable, that is coded it as 0 and 1. That is the loan denied, mortgage denied. So that's why deny represent if we assign 1 for this variable, qualitative variable, if mortgage application is denied, and 0 represent it is accepted. That's why not all the mortgage applications are approved. That is your primary question. Why not all mortgage applications are approved? So hence your focus is on denying the mortgage application. So hence you are coded it as 1. So if the mortgage application is accepted, you have coded it as 0. And the right hand side, the mean and the standard deviations are given. And the second variable is PI ratio, that is anticipated monthly loan payments divided by monthly income. So if a loan application is accepted, or to determine whether a loan application is accepted or not, that depends upon the monthly income of the person or the household. And based on that, the anticipated monthly loan payment or the EMI has been determined. So that's why it is a ratio. It is a ratio kind variable. So the PI ratio refers to anticipated monthly loan payment by monthly income. This is a quantitative variable, quantitative explanatory variable. And the next another independent variable is, since it is related to America, so there is a racial problem. So as of course from last few days you have been of course known the racial problem in America. So of course the same has also be taken here even for these mortgage applications related determination. So whether a person is black or white, that also determines in those countries the applicant's application is accepted or not. That's why here if a person is black, that is denoted or assigned as 1 and 0 otherwise, that is 0 for white. So for our simplicity here we have taken only two independent variables. So in these two independent variables, again one is a quantitative independent variable, the other one is a qualitative independent variable. So hence in any qualitative dependent variable models, so you can have a mix of both quantitative and qualitative variables in your right hand side, but the compulsory is that your dependent variable should be a qualitative one, or it should be a dummy variable one. And in this case it is a binary variable, binary choice type of model. So this is the description of the variables of our model, variables of our study. That is, the dependent variable is a qualitative variable, dependent variable is a qualitative variable, and the one of the independent variable is quantitative, the other independent variable is qualitative. So now let us assume that we have derived or estimated the results for the earlier problem by using Stata, one of the statistical package. Okay, and the results of that Stata is as follows, and we need not of course get into the other part. Let us directly get into these results. Okay, that is the coefficient and the robust standard errors and so on. So in case of that is robust standard, since it is a cross-sectional data, because this is for 2000 plus households for a single period or a single year or a single month or a single year, hence it is a cross-sectional data. So one of the most important problem, of course, as you are noted in the yesterday's class by Niranjan, so the problem of heteroscedasticity we encounter. To overcome from that problem of that is the heteroscedasticity problem, we should have to use the robust estimators. So in Stata, for example, if you just add that robust along with your command, so that gives you the robust standard errors. That means that is corrected the problem of heteroscedasticity, because we were noted that both in case of autocorrelation and also in case of heteroscedasticity, so both these two problems they have an impact on the variances, standard errors. So if that standard errors are corrected because of the presence of the heteroscedasticity or autocorrelation, then your coefficients and your tests, and they are all valid. They are all valid. So and of course, because of that, say the criterion or the idea, the econometricians or statisticians have developed some method of estimations where in estimation itself the standard errors have been corrected, and they produces the good estimates or the blue estimates. So of course, I don't want to get into that part of methods of estimation. So our focus here is that, so the interpretation of this the linear probability model related to our example. And here of course only one variable, only quantitative variable has been taken, and that is the influence of that is the PI ratio, that is the anticipated monthly installment divided by income on the mortgage application has been taken, and the results are this. So the deny is the dependent variable, so this is independent variable, this is the intercept or the constant of our regression equation, as usual in case of your quantitative dependent variable model. And the coefficients are like this. So the coefficient for the quantitative independent variable is 0.060 plus, and the constant is that the respective standard errors, t values, probability values, and the confidence interval about 95% are given in the last two columns of this results. So the estimated OLS coefficient, and another important point which of course we should have to be noted here is that, so we are continue to use the same method of estimation, OLS, that is the ordinary least square method of estimation, is here used to estimate the LPM, because earlier I have told you that it is a linear model. I hope you know that the least square method of estimation is a method of estimation which is appropriate for linear regression models. Since our probability model in this situation is also a linear probability model, then we can continue with use of that OLS. Since the method of estimation we have been used here is the OLS or the least square estimation, hence this 0.06 coefficient is estimated from the least square method, and it is the payment income ratio equal to 0.60. Then the estimated coefficient is statistically different from 0 at 1% level of significance by observing its probability value. The probability value of this PI ratio is 0.00. That means there is a significant influence of this PI ratio on the dependent variable. And how should we interpret this? So how should we interpret it? Because earlier you have noted that you cannot interpret 1%, that is 1 unit increase in the PI ratio that leads to so much of increase or decrease in dependent variable. So you cannot continue with that method of interpretation of this probability models or this qualitative response variable models, as we already noted that. Then how should we interpret this? So we have to interpret based on this, as we already noted that it is the conditional expectation equal to the probability that y is equal to 1, conditional on the given values of x. And of course here we have only one independent variable, that is p bar, PI ratio. Then the population coefficient in case of a multiple linear probability model beta j equals the change in the probability that y is equal to or y is equal to 1 associated with any change in xij. So I hope you are familiar with this. Even in case of your multiple regression model, it is the probability and the partial differentiation of the probability. That is the partial differentiation of the probability of y I given y is equal to 1 given the values of the x with respect to the probability of that is the partial differentiation of xj. So that means if you have several independent variables, so you are able to estimate the probability of the occurrence of your dependent variable, that is the y is equal to 1 for x1 variable, for x2 variable, for x3 variable. That is, we are making use of partial derivatives to derive that coefficient of beta 1, beta 2, beta 3, and so on in this linear probability model. So in case of our mortgage application example, as we already noted that our estimated value of the beta 1 hat, our estimated value of the beta 1, that is the beta 1 hat, is 0.60. The interpretation of this beta 1 hat is a change in the payment to income ratio by 1 is estimated to increase the probability that the mortgage application is denied by 0.60. 0.60. So this is the way which you should have to interpret the result of this binary model or the LPM model. A change in the payment to income ratio, that is your independent. If your independent variable is changed by 1 unit, so that is the probability, since the estimated value of this is positive, no, that's why the probability that the mortgage application is denied by 0.60, and this is the way which you should have to interpret this result. And as earlier I have told you that, so because of that assumption of linear method of estimation and use the least square method of estimation for this, so uh, this LPM model or linear probability model is not used in practice because it violates several conditions of the theory of probability. So hence, of course, we need not get into much about this linear probability. We will take the other popular models which are have been popular and widely used in practice, like logit model and probit model. So after this linear probability model, okay. Uh, so then, okay, then uh, why this linear probability model? Okay, why this linear probability model is not familiar in practice? Why it is not practically applicable in many situations? So here are some problems of this linear probability model. Okay, then the four important such problems are as follows. The first one is the LPM assumes that the probability of the outcome of the model linearity with the value of the explanatory variables okay, with the explanatory moves linearly with the explanatory variables, no matter how small or large that the value is. So that means earlier I have told you that this is a linear model. We have specified the nature of the explanatory variables or the parameters of our model as linear, but that is not the case in practice. Always, if you enter into the probability analysis, always the probability is non-linear in nature. So hence the probability is not linear in nature. The second one is the probability value must always lies between 0 to 1. Yet there is no guarantee that the estimated probability value from this linear probability model will lie within these limits. I hope all of you knew that. The range of values of the probability any for any occurrence or any event that lies always between 0 to 1. 0 represent non-occurrence, 1 represent the certainty of that event, or the event certainly occurs. So always the value of the probability lies between 0 to 1, but if you estimate or make use this LPM model, in some cases the probability might be negative and probability might be greater than 1. So hence that violates the assumption or the violate the condition of that probability theorem, that lies between 0 to 1. The third limitation or the problem with the use of this LPM model is the usual assumption that the error term is normally distributed. So as we already noted, that to use that least square method, you should have to assume your error term of the distribution of your error term is normal. Hence, in linear probability model, the normal distribution has been assumed. But when a dependent variable takes the values of 0 and 1, that never follows the normal distribution. So always these kinds of 0-1 type of models, 0-1 type of variables follows the binomial distribution. So hence that normality assumption is also violated by this LPM model. So then the another problem is the error term in this LPM model is heteroscedastic, making the traditional significance stats suspect. So as of course you have noted from Niranjan class, the implication of heteroscedasticity, the same kind of problem we will face in this LPM model. So because of these reasons, the four important problems. The first one is the assumption of linearity is violated by the probability concept. The second one is in some situations, in some practical problems, so the probability estimated by this LPM model violates that condition of probability that should be lies between 0 to 1. The third assumption of normality of the error term is also not met by this types of dummy dependent variable models. And the last but not the least is, so this LPM model is suffer from the heteroscedastic problems. So because of these problems, econometricians have been developed an advanced model over this LPM model, and that model is the logit and profit models. Logit and profit models. So now let us have again a discussion of those logit and profit models. Logit and profit models, and of course this is how this LPM model violates that assumption of the condition for the probability that should be lies between 0 to 1. So this is the zero value. This is the probability of the mortgage application denied is this, mortgage application is accepted this. And another important point by observation of this slide, you should have to bear in your mind, in case of your quantitative dependent variable along with a quantitative independent and qualitative independent variables. So I hope if you have represent your data in terms of a scatter diagram, so your scatters are distributed. Your scatters are distributed and may have some specific pattern of increasing pattern or decreasing pattern. But for all these dummy-dependent variable models, especially for this binary choice of models, so your scatter points are clustered like this, because the value taken by your dependent variable is only 2, 0 and 1. So that's why all the values are clustered here. So since of course they are also called as censored here. So this is censored in the 0 part and censored in the 1 with a probability of 1 and its probability of 0. So this 0 represent, or these dot points represent, so the persons who are denied mortgage applications or loan, whereas these data points represent who are accepted or say provided loan. So that's why mortgage, in case of our analysis, we have mortgage denied, we have assigned 1 for mortgage denied, that's why this is the mortgage denied, and 0 for mortgage approved. So but the point is, so you have only two values, 0 and 1, and if you fit a linear probability model, your linear probability model passes like this. So if you calculate the distance between this, so your error is too large, or in other words, it is not a good fit. In terms of that. And but moreover, the point here is that, so your estimated linear probability model crosses these bounds, 0 bound and 1 bound. So it is this part represent the probability is greater than 1, and a part below this of this curve represent the probability is negative, but theoretically it is impossible. So because of these reasons, this linear probability model has not been used in practice, though it is simple compared to the logit and probit models. Okay, I hope this is enough related to the first model of qualitative dependent variable, that is the that is the linear probability model as a base for our the advanced models of logit and probit models. So the same is of course one more illustrative example. Some values are negative and some values are positive. That violates that condition of the probability always should be lies between 0 to 1. Okay, this is about a brief discussion on introduction to qualitative dependent variable model or qualitative response variable models, and the first modeling of that qualitative dependent variable, that is the linear probability model. So okay, now let us enter into the next model, that is linear, that is the logistic regression model or logit model or logit regression. These are the synonymous names I hope you have been seeing in the literature. This is called as logit model, logit regression, or logistic regression. And even within this logistic regression, so that can be used in different situations. So logistic regression, which we are using or discussing now, is only for a binary variable. Hence it is a binary logistic regression, ordered logistic regression, multinomial logistic regression, the logistic regression for panel data. So these are the logistic regression model used for different types of data and the classifications of the data. So if you have only two classifications of your dummy dependent variable, that is called as binary logistic or dichotomous logistic regression model. If your dependent variable is classified into several classes, several categories, several choices you have. For example, the preference of transportation, that is the travel to work, whether a person travel, which mode of transportation he has been used to travel from his home to workplace, whether by walk or by car or by public transportation. Now you have more than two choices. So it is called as multi-choice models or multinomial models, generally called in statistics and also in econometrics. So if you use again the logistic model can be used for that, but that is called as multinomial logistic model. So there are some variables, they are also dependent variables, and also they are qualitative variables. So those qualitative variables can be ordered. I hope as I already told you that. So you have studied that part in your statistics related to classifications of the variables on the basis of the measurement scale, that is ordinal variables. So if you have such an ordinal variable, so if you use to determine the value or expected value of that ordered or ordinal variable, then you have ordinal logistic regression. So that's why the application of this logistic regression is wide, based on the circumstance, based on the appropriateness, and based on the type of the data you have. Out of all these, okay, the variants of the logistic regression model and its applications, now we are discussing the simplest part of that, that is the application of this logistic model for binary choice models or dichotomous dummy dependent variables. Okay, so now have a brief discussion on this. The better alternative to that LPM model is the logistic regression. So because of the four important problems which you have been discussed just now regarding the LPM, of course, by using some heteroscedastic corrected standard errors, we can correct the problem of heteroscedasticity. So if you increase our sample size due to because of invoke of the central limit theorem, your variable follows the normal distribution. I hope all of you knew that central limit theorem in statistics. So that means if you goes on increasing your sample size indefinitely, all the distributions follows the normal distribution. So that is called as central limit theorem. So by that invoke of central limit theorem, that problem of say the binary distribution or binomial distribution can be solved by using large number of applications. But you cannot solve that probability. Lies uh, lies above one and below one in the LPM model. So because of this reason, so a best alternative is required, and the best alternative to that LPM model is the logistic regression model. And in literature, this model is familiar with the word logit, that is the logit model. This logit model is a nonlinear model. So a nonlinear form of regression that works well for dichotomous dependent variables. So hence it is a better alternative. It taken care of all the problems of that LPM model. So LPM model. And the other nonlinear formulation also works, that is probit model. So hence there are two better alternatives for that LPM model. The one is logit model, the other one is probit model. So they are, both of them are widely used, popular, but according to Amemia, one great econometrician, and he said once regarding the choice of this logit and probit model. So there is no any rule of thumb to determine our choice over logit to probit or probit to logit. So that's why that depends upon the researcher and the data he has. Based on that circumstance and situation, the researcher can choose logit or probit model, though the method of estimations are different and the methodological interpretations of these two models are different and the values which we have estimated are different. But we if we obtain the marginal effect coefficients, so then the marginal effects coefficients are more or less same between the logit and probit model. And hence my discussion related to this logit and probit model more focus is on logit model and less on probit analysis. So more or less they are one and the same in terms of their estimated marginal effects. Okay, so if I go back to my discussion, the better alternative to that LPM model are logit and probit models. So this logit model is based on the odds rather than the probability. Odds rather than the probability. That's why I've told you that you should have to have some basic knowledge of probability to understand these qualitative dependent variable models. So along with that probability, now we have one more phenomenon of that probability concept, that is odds. So the LPM model was based on probability, whereas this logistic regression model is based on odds rather than probability. So rather than the modeling that is probability of y is equal to 1, we model the logs odds of y is equal to 1. That means in case of your LPM model, you have written in your dependent variable as a probability of y is equal to 1 given x and so on. But whereas in case of logit model, so the form of the or the formulation of your dependent variable, configuration of your dependent variable is in terms of log odds ratio or log odds. That is, logit refers to the natural log of odds. So that's why the name for this model is given as logit model. So we have selected, or we have to compute the odd ratio first, and we should have to take the natural log of that odds. So because of that natural log of the odds of the occurrence of the event, we call it as a logit model or logistic model. So the logistic regression is a regression for a logit. So why again why we call it as a logistic regression? Because this is a regression for logit. Your dependent variable or the form of your dependent variable is in logit form, and you are estimating the effect of a given independent variables and their influence on the logit form of the dependent variable. Hence it is also known as logistic regression. Logistic regression. So rather than a simple variable y. In case of your simple and multiple regression model, your dependent variable was only y. Whereas in LPM, it is probability of y is equal to 1. Whereas in case of logistic regression or logit model, it is the logit of the dependent variable or the natural log of the odds of the dependent variable. Natural log of the odds of the dependent variable. So this is the difference between the configuration of the dependent variable, the formulation of the dependent variable between the simple regression model or the OLS methodology with the linear probability model and the logistic model. Logistic model.
Sir, could you please enlarge your screen, sir?
Oh, yeah. Okay. Slide, so I should have to start.
Yes, sir.
Now it's okay?
Yes, sir. Thank you very much, sir.
Okay. Now, so this is the difference between the left-hand side of our equations in case of OLS methodology, LPM, and logistic regression. Okay, in case of so the OLS are our simple and multiple regression model, we have written our dependent variable as only y. Whereas in case of LPM model, it is only as probability. The probability of y is equal to 1. Whereas in case of this logit model or logistic regression model, our dependent variable is natural log of odds. Natural log of odds. So hence this model is called as logistic regression or logit model. Logit model. Okay. So then in the earlier slide, you are come across with the two phenomenons. One is probability and the odds of probability, or only odds. So now let us have define the probability and odds. So you know very well about the definition of a probability. For example, if the event is A, then the probability of event A is defined as the P of A is the outcomes in which A occurs divided by the total number of the outcomes. For example, if you toss a coin, by flipping a coin, you would get two events, head and tail. That is the total number of the events. Out of the total number of the event, you are expected or you are expecting one among the outcomes or one among the occurring events. For example, if you are expecting the occurrence of the head, then the probability of head is, that is, the outcomes in A occurs. A is head occurs. So you know that out of the two outcomes, only one is head. Then the probability of head is 1 by 2. But a general definition is, and of course, that's why I've told you that you should have to have a basic knowledge of probability to understand these dummy-dependent variable models, because there are basic concepts, core phenomenons in probability analysis. So like a random experiment, then sample space, mutually exclusive events, mutually exhaustive events, simple events, independent events, then dependent events, and so on, so on. So you should, again, to understand this dummy dependent variable regression models, so you should have to well versed with that probability basic phenomenons, and based on that knowledge, we have defined the probability as, so if you have to do an experiment, that experiment produces outcome. So the flipping a coin is also an experiment that produces two outcomes, head and tail. Out of those two outcomes, our purpose is to predict or to estimate the probability of occurrence of one of the event. So based on that process of the random experiment, the probability has been defined here as outcomes in which A occurs, and that should be divided by the total number of the events. But the same, of course, example is given. That is the coin flip. Probability of heads is, the one outcome is head. That out of two possible outcomes, then the probability of heads is equal to 1 by 2. In terms of ratio, it is 0.5. But now, based on that concept of probability, now we are defining odds. Odds of A. Odds of A means the event A. The odds of A is equal to the number of the outcomes that are A divided by the number of the outcomes that are not A. So I hope you got the idea between the probability and the odds. In case of calculation of the probability, it is a ratio of the outcomes of your favorable events or occurrences divided by the total number of the events or occurrences. But whereas in case of the odds of the A, it is only related to the A element or the A outcome. Hence, the odds of A is the number of the outcomes that are A divided by the number of the outcomes that are not A. So in case of heads, okay, the odds of heads is 1 divided by 1. So because since you have only two outcomes, so out of the two outcomes, one is the number of the outcome A is head divided by not the head occurs is also 1, which is equal to 1 by 1 by 1, which is equal to 1. Also equivalent to the probability of event over the probability of it not happening. So that is, so how to define these odds? It is equivalent to the probability of occurrence of an event or the probability of occurrence of not occurrence of the event. That is the odds. That is the odds. So the probability of occurrence of the event divided by the probability of not occurrence of the event, or the probability of the event over happening to it not over happening. So that is the probability divided by 1 minus probability, that is 0.5, is the occurrence of the head is 0.5, not occurrence is 1 minus probability of the occurrence, that is 1 minus 0.5, which is equal to 1, which is equal to 1. So that's why the odds is defined as the number of the outcomes that are A divided by the number of the outcomes that are not A, or the probability of event over probability of event over probability of it not happening. It is not happening. This is the definition of odds. This is the definition of odds. So then in case of logistic regression model, we have to convert this probability into odds, and this is the odds. So symbolically, that odds is equal to pi, that is the probability of occurrence of the event, divided by the probability of not occurrence of the event is 1 minus probability. So then we should have to take the natural log of this odds. Then we call it as logit. That's why the natural log of an odd is logit. That is, the natural log means a base of e, not base n. Because I hope all of you knew that there are two logarithms in mathematics. One is a log with a common log, and the other one is natural logarithm. So the base for the common log is 10, whereas the base for the e is the 2.37 something like that. Okay, so that's why here we are using natural log. So if you take the natural log of odds, that is called as logit. So we can model a logit as a function of independent variables. You can model a logit as a function of independent variables. Just we model y or a probability in case of OLS and the LPM models. So that's why I've told you that your dependent variable is in logit form. This logit means it is the logit form of your probability in odds form, or your dependent variable now is pi divided by 1 minus pi, and which is in natural logarithmic representation. So this is the configuration or the formulation of the left hand side of our logistic regression or our qualitative dependent variable. And we have noted that how this is different from our OLS model and the linear probability model. So this is the logit of P. This logit of P, which can be written as Li. This Li refers to logit of P. So this Li again can be written as natural log of odd. Natural log of odds. The odds means pi divided by 1 minus pi. So that's why you can written your left hand side in these three forms: logit of the P, or just Li, or the natural log of odds, pi divided by 1 minus p, which is equivalent to the same, because the right hand side of your equation is similar in our earlier case as a function of independent variables. So here the natural log of the odds depends upon the determinants, depends upon the given values of the explanatory variables x's, that is intercept of your regression is alpha, and your variables are from 1 to k with their respective coefficients or the parameters. So this is a logistic regression or logit model. So your simple regression or the multiple regression model with your least square method is y is equal to alpha plus beta 1 plus beta 1 plus beta 2 x1 plus beta 2 x3 and so on. Whereas in case of your linear probability model, your dependent variable is probability of y is equal to 1, which is equal to beta 1 plus beta 2 xi and so on. Whereas your logistic regression model or the logit model is natural log of pi divided by 1 minus pi, which is equal to same of the right hand side of your earlier equations or earlier methodologies, regressions of OLS and the LPM. That's why only the difference or the configurations which we have made into the left hand side, almost the right hand side of all the three models are one and the same. Why we need this natural log of you should have to remember here, or you should have to remember the limitation of the LPM model. So one of the most important limitation earlier we have noted that the LPM that violates that condition of probability lies between 0 to 1. But if you convert your probability into odds and take the natural log of that odds, your estimated probabilities are bounded between 0 and 1. 1. It never crosses these bounds. So never the probability value calculated by this logistic regression model is negative, below 0, or greater than 1. So because of this reason, you should have to convert your probability into odds ratio or odds. Then you should have to again transform that odds into natural log. The reason is to confine your estimated probabilities between the two bounds of 0 and 1. 0 and 1. That is the crux. And of course, the same is shown here with this diagrammatical representation of logit model. Just to remember or recap that linear probability curve. So linear probability curve that crosses 0 and 1 boundary, but here it is not. It is a different shape. And mathematically, this shape or these kinds of shapes and the functional form of these shapes are called as the sigmoid functions. They are called as sigmoid functions or S-shaped functions. S-shaped functions, or technically they are called as sigmoid functions. There are different types of sigmoid functions. Our logistic model is one of the sigmoid function. So because of this nature of the sigmoid function, the estimated probabilities from this logistic regression model lies between only 0 to 1. Just keep this point in your mind related to this, how this logistic regression model corrects that problem of violation of the theoretical condition of the magnitude of the probability. And of course, now we are comparing this logistic regression model with linear probability model. So logistic regression model never crosses these bounds, whereas the linear probability model may have negative values or negative probability values are greater than 1 in some situations. So because of this, the logistic regression model is a better compared to the linear probability model, as we already noted. And and of course, there are mathematical technicalities are involved in specification of the logistic regression model. We need not get into that mathematical technicalities. So the specific, for example, model or modeling or the equation which we written it by some manipulation of by manipulation of that model is like this. There is the probability of y given x, the probability of y given x, which is equivalent to 1 divided by 1 plus e to the power minus this. This is our regression, right hand side of the regression model. E already we have noted that is the natural log. So we have converted our alpha plus summation I j to k and so on into this nonlinear form, and this is the shape of this. And of course, this is a curve which is estimated, logistic curve which is estimated for the two variables. The one is whether a person has the problem of cholesterol or not. That is depends upon age also. That means whether a person has a problem of cholesterol disease or not. That is the probability of cholesterol disease. The vertical axis measures the probability of the cholesterol disease. That probability of the cholesterol disease depends upon the age of the person. And as we were noted, based on our common sense, as the age of the person increases, the probability of the cholesterol disease increases. So hence, whether a person has a cholesterol disease or not, that becomes our dependent variable, that is assumed to be determined by the age of the person. So hence, the dependent variable is the probability of the cholesterol disease and depends upon the age rate. And if you take a logistic regression, so that logistic regression looks like this, and this regression is derived from this mathematical representation. And these are the things, as earlier I have told you, that the mathematical. So actually we have ended with this. Earlier I have shown you that. So to derive this specification, so we have to manipulate our logistic regression like this. We should have to take the exponent of both the p, and this is 1 minus p. Okay, then we have make some further manipulations, and finally we would get a an estimable form of logistic regression with like this log of y divided by 1 minus y, or with this. So they are equivalent. They are equivalent forms of the value of the dependent variable and the right hand side of our independent variables in case of our logistic regression model. And these are the again the reformulations. I don't want to get into this. Okay, so because purpose, that is the pi divided by 1 minus pi and its natural log cannot be directly used for estimable purposes. So hence finally we resolve that probability and reformulate the model like this: probability of y is equal to 1 with this, and based on this we finally have ln pi divided by 1 minus p, a formulation of your dependent variable for estimable purposes or estimation of the regression coefficients of this logistic regression model. So this is about an introduction to logistic regression model and the specification or modeling logistic regression model. So once we have modeled our regression as the probability of, that is the probability of y is equal to 1 as 1 divided by 1 plus e to the power, that is beta naught plus beta 1 x1 plus beta 2 x2 and so on. That is your logistic regression. So then how to estimate this logistic regression model? So what method of estimation we should have to use? So in the earlier case, in the y is a function of so and so, and your probability of y is equal to 1 in case of your LPM, as we already noted, we have used the least squares method. But that cannot be continued here because the reason is your regression model now we have specified under this logistic regression is not a linear one. It is purely a non-linear regression model. I hope you remember the basics of that regression analysis in your classes of econometrics. So we cannot use ordinary least square method for estimation purpose of non-linear regressions. Logistic model is a non-linear regression model, hence we cannot use least squares method. And this is so how this least square method works is given here, and we cannot use that least square method, hence we should have to use a best alternative to that least square method, that is the maximum likelihood estimation. So hence the estimation of regression of this logistic model is estimated by the maximum likelihood estimation. And this is the form. Earlier also I have told you that Li hat is, it is the logit of pi divided by 1 minus p, r, which is equivalent to probability of y is equal to 1. So that can be estimated like this. And the maximum likelihood estimation is used to get the solution for this type of model. And I don't want to get into that part, how this maximum likelihood estimation works. Most of the statistical packages produces the results of this logistic regression model by making use of the maximum likelihood estimation. Okay, so then and of course how this the maximum likelihood estimation is better for nonlinear regression compared to the OLS. So of course they are given here. The maximum likelihood estimation is consistent, efficient, and also it is asymptotically normal as n approaches to infinity. And always you should have to use this maximum likelihood estimation only for the larger samples. If you use maximum likelihood estimation for small samples, your estimators are not robust, or they might be inconsistent. So hence always we should have to use a large number of observations in case of logistic regression analysis to use this maximum likelihood estimation. And this is about a method of estimation of logistic regression. There are some rules of thumbs related to number of the observations which are required in case of logistic model in particular, or generally in case of use of this maximum likelihood estimation. You should have to go through the literature related to that conditions for sample size for the use of this maximum likelihood estimation in general, and in particular in case of logistic regression analysis. logistic regression analysis. And of course, as we already noted, the benefits of logistic regression compared to the previous method of estimation of this qualitative dependent variable model. So you can now effectively model probability as a function of X variable. You do not have to worry about the violation of the assumptions, and prediction fall between 0 and 1. That means all the conditions which we were earlier noted has been satisfied by the logistic regression model, and hence this logistic regression model has several benefits compared to other method of estimations, especially the linear probability model in case of dummy dependent variable models. Downsides, that is the limitations are the most important